all the points related to geometrical isomerism like cis-trans isomerism or cis-trans configuration and EZ configuration. In addition, we saw what is whether the cis-trans isomerism is observed only with alkenes or it can be observed in alkenes also. The main cause behind this configuration pattern is that there is some sort of restriction in rotation. Okay. Now let us see the geometrical isomerism in case of oximes. What are these oximes? When there is condensation of carbonyl functional group with hydroxylamine, what will happen? कार्बोनिल ग्रुप जब कभी भी NH2 ग्रुप के साथ रिएक्ट करता है वाटर मॉलिक्यूल लिबरेट हो जाता है. एंड हाउ दिस वाटर मॉलिक्यूल इज लिबरेटेड? दिस टू हाइड्रोजन्स एंड दिस ऑक्सीजन, they will form the water molecule, and this nitrogen will go and get attached over here, and we will get a resultant molecule like this. Okay. Now here you can observe water molecule is liberated out and we get a compound like this. This compound is called as hydroxylamine derivative of the carbonyl compound, or in short we can call it as the oxime of the parent carbonyl compound. If at all it would have been aldehyde, then this would have been called as aldoxime. If it is a ketone, then we call it as ketoxime. If at all it is acetaldehyde, in that case acetaldehyde oxime. Okay. So we can I think you have come across this type of reaction when you studied your POC1 in second semester of B Pharmacy course. These compounds, they have got a doubly bonded nitrogen atom. Till now we saw double bonded or doubly bonded carbon atoms only. Here the main point to observe is that here the double bond is not associated with carbon atoms on both the sides. On one side a carbon atom and on the other side a nitrogen atom is there. Okay. Of course, as it is a double bond bearing molecule, it is supposed to show sp2 hybridization, and because of the existence of sp2 hybridization, it is quite similar to that of alkenes. However, there is some difference. The way alkenes show geometrical isomerism, aldoximes or ketoximes, or to be specific, oximes also show geometrical isomerism. How we have to differentiate them? Can we differentiate them as cis-trans or EZ? Here we do not have two sides, isn't it? The way in case of carbon we used to observe. In case of oximes, we can say, as I have told you in the earlier slide, oximes can be of two types, that is aldoxime and ketoxime. If one of these two functional groups becomes an oximes as shown below. Here we can see the oxime double bond bearing nitrogen, double bond bearing carbon. This carbon is associated with two alkyl groups. These two alkyl groups are given. Configuration of this oxime is R dash and OH. They are lying on opposite side. Here, instead of cis trans term or instead of using EZ term, the two configurations they can be represented by the term or by the descriptors syn and anti. Okay, so we can say the descriptors syn and anti are used to distinguish the configurations observed in case of the hydroxyl group. If at all we are talking about aldoxime, that means one of these R and R dash is hydrogen. If hydrogen and hydroxyl group, they lie on same side, that is they are on the same side of the carbon nitrogen double bond, we call it as syn. Okay, whereas if the hydrogen and the hydroxyl group, hydrogen atom attached to the carbon atom and the hydroxyl group attached to the nitrogen atom, they lie opposite to each other, we call it as antiform. Okay, here now try to differentiate or try to find out whether this configuration represents syn or anti-configuration. Here H and OH, they lie on same side. It is denoted as syn oxime. Here H and OH, they are lying on opposite side, hence anti-oxime. Okay, syn and anti-oxime is easy to differentiate in case of aldoximes because one hydrogen is present in case of aldoxime. If we talk about ketoxime, what will happen? Here instead of H, it means यहाँ पे क्या बोला गया है? When we talk about ketoxime, whichever name of these two functional groups, whichever is cited first, if that cited first group lies on the same side of the OH, on the same side as the OH group, then we will call it as syn molecule or syn type of configuration. If the functional group which is cited first, it lies opposite to OH group, in that case we will call it as anti-configuration. Now let us see this molecule. It is ethyl methyl ketone. On one side methyl group, on one side ethyl group. Now if we see the ethyl group and the OH functional group, they lie opposite to each other. Now if the name of or of this two functional group, if methyl term is cited first, then we can say methyl group and OH group, they lie on same side, hence it is syn configuration. Likewise, if in the structure or if in the description of the molecule ethyl group is cited first, in that case ethyl group, we can see here ethyl group and OH group, they lie opposite to each other, hence we'll call the same thing as anti-ketoxime. So it is dependent on the group which is cited first. The geometrical isomers are, in short, EZ notations of oximes can be described as the geometrical isomers which are better differentiated by using EZ notations. The Z oxime has hydroxyl group and the group with higher priority on the same side of carbon nitrogen double bond. However, in case of oximes, they are, or E oximes, they are arranged on the opposite sides of the carbon-nitrogen double bond. The syn acetaldoxime is denoted, or it is named as E-acetaldoxime. Okay, now if we see this structure, here it is aldoxine, hydrogen, and if at all it is aldoxine, in that case we have to compare the relative position of hydrogen atom attached to the doubly bonded carbon and the OH functional group attached to the nitrogen. If we see their orientation, we can find or observe hydrogen and OH group. They lie on the same side. Hence, it is a syn isomer or syn configuration. However, when we talk about EZ nomenclature, in that case, or EZ designation, we can find out that of these two, CH3 group has got higher priority as compared to hydrogen, and they're like opposite. Hence it is E isomer or E configuration. That is, to be specific, when we name this structure, it is N-hydroxyl or N-hydroxy ethanamine. That is amine which is having a double bond, hence imine. It is N-hydroxy ethanamine or ethanimine. Clear? Here it is representing syn form. However, if we denote this in terms of E or Z notation, then it is denoted as 1E N-hydroxy ethanamine. The antiform of aldoxine will be like this. Here, high priority functional group, they lie on same side. Hence, Z, that is same or same side. Or high priority bearing functional group, they lie together, or they lie on the same side of the plane, double bond bearing plane. The name remains the same. However, the orientation over here is different. And how it is different? Here it is placed. It is just flipped to this side. We can denote this antiform. We can denote this as antiform, and in its IPAC nomenclature, it will be denoted as 1Z N-hydroxy ethanimine. Clear?
Yes, ma'am.
Now, when we talked about this geometrical isomerism, we talked about terms like configuration and conformations. What are these configurations and conformations? First, let us understand the terms. What is the meaning of configuration, and what is the meaning of conformation? What is configuration? Configuration of a molecule is the spatial arrangement of atoms and groups about a rigid part of the molecule. And which rigid part is usually taken into consideration during configuration study? It is about the double bond or ज्योमेट्रिकल आइसोमेरिज्म और कहाँ पे देखने को मिलता है सिस ट्रांस आइसोमेरिज्म के अपार्ट फ्रॉम दिस डबली बॉन्डेड एटम्स कार्बन कार्बन बॉन्ड it is also observed in case of cycloalkanes, that is ring like structures. And note it, these configurations are not interconvertible. Why they are not interconvertible? Because of their restricted rotation about the rigid part of the molecule, and they can be represented by either Fischer projection method or wedge bond projection method. Basically, or broadly speaking, these configurations are of two types. What are they? First is relative configuration and second is absolute configuration. The configuration of a molecule about a asymmetric center is called as its relative configuration, or we can say, in other words, relative configuration is the configuration of a molecule about an asymmetric center. Clear है? What is relative configuration? Relative configuration is the configuration about an asymmetric center or an asymmetric carbon atom. There are two types of relative configuration. हमने पहले भी देखा हुआ था when we talked about DL isomerism or DL stereoisomers or arytro and trio forms of enantiomers. That time we came across these type of configurations. What is arytro and trio form? D and L. Do you remember the carbohydrates, amino acids, molecules we discussed in detail when we discussed optical isomerism or stereoisomerism of unit 1. In case of D, all the OH groups, they were lying on one side, or similar functional groups were lying on one side. L, it was different then, or it was opposite to D type. Arytro and trio, if similar functional groups, they are lying on same side of the chiral carbon or chirality center, we called it as arytro. If they were representing up, or they were presenting on they were present on opposite sides, then we called it as trio forms of the configuration. Now let us see what is absolute configuration. What this absolute configuration means? Absolute configuration is the spatial arrangement of the groups in a chiral molecule, which distinguishes it from its mirror image. Okay, when we talk about absolute configurations are of two types. First one is RS configuration, which is generally observed with chiral molecules or molecules having more than one chiral centers, and EZ nomenclature or EZ bearing configurations are usually observed when there is a rigid site in the molecule, that is either a double bond between carbon-carbon atom, or a double bond between carbon and nitrogen atom, or a ring-like cycloalkane structure. Okay, so to summarize, we can say configurations are broadly classified as relative configuration and absolute configuration. Relative configurations are further classified as DL configurations and arytro and trio form of configuration. Whereas when we talk about absolute configuration, it deals with spatial arrangement of groups in a chiral molecule, which distinguishes it from its mirror image. Okay, and they are of two types, R and S type and E and Z type. Now let us see what are conformations. Till now, we learned about configurations. Now let us see what are conformations. Now you just see these three images. What you can observe? Humanoid diagram it is, and it is showing that the human being is dancing. This is in one pose. It is tilted here, and here it is totally inverted or somewhat partially inverted. However, the person remains the same, whether standing straight or standing in some of these orientations. Even then, the person remains the same. It's not it. Now, with this basic concept, let us try to understand what are conformations. Now, conformations are also referred to as conformers or conformational isomers. I repeat, these conformations are also referred to as conformers or conformational isomers. And what they represent? They represent different arrangement of atoms that occur as a result of rotation about a single bond. For example, now let us see these three structures. Now, if we see these structures, let us see these structures one after another. Here, if we see the first structure, this is the main carbon-carbon skeleton. To the first carbon, we can see on one side, chlorine atom is attached, and the orientation of the chlorine atom is such that it is lying above the plane, that is, it is lying towards the observer. Hydrogen atom is lying away from the observer, whereas CH3 is in the plane. Now, if we see the orientation of the functional groups and atoms attached to the second carbon, here we can see OH group lies on the plane of the paper, whereas hydrogen atom is towards the observer, and Br atom or bromine atom is representing, or it is showing away from the observer. Now, if there is a rotation, okay, if we rotate this carbon atom by 120 degree, we have to rotate this axis by 120 degree. If we do that rotation, because it is a sigma bond, we can easily rotate it about this carbon-carbon single bond. When we rotate this by 120 degree, we will get a molecule or a structure like this. Here we can see this part remains the same, whereas this part is changed. And how it is changed? The hydroxyl functional group has now gone below the plane, whereas bromine is pointing towards the observer, whereas H is lying on the plane. These two are lying perpendicular. Okay, that means it is towards the observer, it is away from the observer. If this is the plane, it is up, it is down. Okay. Now, if we rotate this structure further by another 120 degree, what will happen? This remains the same. The orientation of the three functional groups and atoms attached to the first carbon remains the same. However, the orientation of these three changes further. And how the changes are shown? Now what will happen? The OH will come to the position of Br. Here OH is pointing towards the observer. Br or bromine lies on the plane of the paper, whereas H is away from the observer. That is, OH is up, facing up. H is facing down the paper. Br is on the paper. Here CH3, Cl and H. Cl is up the paper, hydrogen is below the paper, plane of the paper, and CH3 is on the plane of the paper. Now, most often these rotations occur very fast because this rotation about single bond or a sigma bond is able to undergo free rotation at room temperature. That is why the conformations are not considered as different compounds. Okay, even though we have rotated it and we have obtained 3 different conformations, however, as because such type of changes, conformational changes, do occur at very frequent intervals at room temperature, we do not consider these 3 conformations as 3 different compounds. For example, whatever pose the man acquires, the man remains the same. So for now, remember that just because the structure looks different, it does not mean that they represent different compounds. We have to see the 3 functional groups and the net, we have to compare the net molecular formula. The 3 functional groups attached to first carbon remains the same in all the cases. The 3 functional groups attached to the second carbon remains the same in all the cases. However, the orientation of the functional groups about one of the carbon atoms is different. Even though they do differ in their orientation or differ in the orientation of the functional groups attached to the molecule, they represent different conformations. However, they represent the same compound. Clear? What is the difference between these 3 things? They are representing the same molecule in different conformations, or we can call them as different conformers, or we can call them as conformational isomers. These conformations, they can be represented or they can be shown by bond line structure or a zigzag structure. Second method is by Sohor's projection, and third method is by Newman projections. The bond line projection is shown like this. Sohor's projection of the same conformer is shown like this, and Newman projection is shown like this. So these are 3 different methods or different ways by which conformations, various conformations can be represented on a 2-dimensional plane or in the plane of a paper. Okay, so with this we come to an end for today, and we will continue from here in the next lecture. That is